In this session, we will learn about matrices and matrix operations in Scilab. We will first explore matrix operations on regular matrices, and then move on to sparse matrix formulations. We will learn how to define matrices, perform elementary operations, and also perform matrix factorizations and solve system of equations. Now, to define a matrix, we have four functions available in Scilab. We can create m by n matrices using these functions. Here, in the script we define four variables a, b, c, d as matrices. Variable a is defined as 5 by 5 matrix using zeros function. Zeros function returns a matrix with all 0 entries in the matrix. Variable b is defined as 3 by 3 matrix using ones function. Ones function returns a matrix with all entries in the matrix as 1. Variable c is defined as 4 by 4 matrix using I function. I function returns a matrix with all entries in the diagonal of the matrix as 1, also known as diagonal matrix. Variable d is defined as a diagonal matrix using diag function. For this we define a vector v which is used as main diagonal of the matrix. We can also define a matrix by using bracket operator. The rows of the matrix are separated by semicolon, and columns are separated by spaces. Here, we list some elementary functions which we can use on a matrix. Let's see them in Scilab. We define a matrix A using random value generator function. Then using the matrix A, we can find maximum and minimum value in the matrix with min and max functions. Then to get the lower or upper triangular matrix, we use tri-L or tri-U functions. Norms are used in error and convergence analysis in scientific computations. We can find L1 norm, infinity norm, and Frobenius norm in Scilab. Matrix shaping functions are used to resize or find the shape of the matrix. Using resize function, we can increase or decrease the rows and columns of the matrix. Using matrix function, we can reshape the matrix and rearrange the elements of the matrix. We can also find the type of matrix object, using the shape testing functions like isColumn, isRow, or isSquare matrix. Using the size function, we can get the number of rows and columns of the matrix. Here, we define a 2 by 2 matrix A. Now using the resize matrix function, we increase the rows by 2 and columns by 2, to get a 4 by 4 matrix. The elements of the matrix are kept same and size of the matrix is increased. Now, we define a 6 by 1 row matrix A. Now we will convert this matrix into a 3 by 2 matrix, using matrix function, which will change the rows and columns and reorder the elements of the matrix A. Now, we will perform some basic linear algebraic operations on matrix objects. We can compute inverse, determinant, trace, rank and condition number of a matrix. Rank of a matrix indicates how many rows and columns are unique, and not linear combination of other rows or columns. For scientific calculations like finite element methods, matrix rank plays important role. Rank should be equal to the number of rows of the matrix or else its determinant will be 0. Condition number is used in numerical calculations. Matrices of linear systems with high condition number are almost singular, and said to be ill-conditioned, and do not have unique solutions, and its determinant will be 0. Here, we define a matrix A, and perform the basic operations like calculating the determinant, trace, which is sum of diagonal elements of A. Then we find inverse, rank, and condition number of A. In the console we can see the results of these operations. Spec function calculates all the eigenvalues and corresponding eigenvectors of the matrix. Eigenvalues and eigenvectors are also called characteristic values and characteristic vectors. Any matrix of size n, having n real eigenvalues, is called positive definite matrix. If the matrix has 0 as eigenvalue, then the matrix is singular, and has very high condition number, and 0 determinant. In electrical systems, eigenvalues are used in circuit analysis to find the response of second or higher order systems. In structural mechanics, eigenvalue of a matrix is the measure of the frequency of the vibration of a body, and eigenvector is the corresponding mode shape. For very large matrices which are found in numerical methods like FEM, we only need to calculate first few eigenvalues of the system, so this function is not used, and other advanced methods like vector iteration and subspace iteration methods are used. Now, we define a matrix A, and using the spec function, we get the eigenvalues and eigenvectors of the matrix, and display it in the console. We observe that one of the eigenvalue is 0, so it is not a positive definite system. Now, if we calculate determinant of this matrix, it is 0, and condition number is very high. Factorization of a matrix is decomposing a single matrix into two or more matrices. Only non-singular matrix, whose determinant is non-zero, can be factored into separate matrices. In Scilab we can factorize the matrix using these functions. Function ShowL performs factorization of positive definite matrix A, using Cholesky algorithm, and returns upper triangular matrix. LU function decomposes a general matrix A into lower and upper triangular matrices. QR function decomposes the matrix into orthogonal matrix Q and upper triangular matrix R. It is used in least square solutions of linear systems, where the system matrix is decomposed to canonical forms, via orthogonal transformations. Here, we define a matrix A, and perform the factorization of A, using the three functions which we discussed. The results of the factorization is displayed in the console. Factorization is used in solving linear system of equations, where the coefficient matrix A is factorized, using any of these algorithms based on its condition. Now, we look at the solution of n linear, algebraic equations in n unknowns. A system of algebraic equations has the form as shown, where the coefficients of matrix A and B are known, and vector x is unknown. The system has unique solution if the coefficient matrix A is non-singular, and has condition number close to unity. In Scilab, we can solve such systems using backslash operator, also known as left division operator, where we divide matrix A by vector B, and the solution x will be computed either from LU factorization for well-conditioned problems, or from a linear least squares solver, using QR factorization of A, for ill-conditioned problems. We can also use linsolve function, which only takes linear coefficient matrix A and returns the solution. Here, we solve a very simple problem of circuits. We apply Kirchhoff's current rule at each node, and we get 6 equations, with 6 unknown currents. Here, we define the 6 by 6 coefficient matrix A. Then we define vector B. Using the backslash operator, we solve the system of equations and get the current flowing in the circuit. Now, we will see how to extract and modify elements from a matrix, get rows or columns as vectors, and add new rows and columns to a matrix. First we define a matrix A. Then, to get the elements of the matrix, we assign the value of the matrix element at the location given by the row and column index. Variable A11 will be assigned a value located at first row and first column, variable A22 will be first row second column, and so on. Now, to change the value of any element in the matrix, we modify the value of the matrix element at the location given by the row and column index. Now, we want to get the first row into a vector. For that we use the colon operator. To get the complete row, we specify the row index and put colon operator in the place for column index. Likewise, we can get the columns by putting colon operator in place of row index. We see that variable R1 is a row vector with all elements of first row, and variable C1 is a column vector with all elements of first column. We can also specify range of columns or rows, instead of all, by specifying the index range. Now, we want to add new row and column to the matrix A. To add new rows or columns, we use square brackets operator. Inside the brackets, the first entry is the matrix variable A, and second entry is the new row or column variable. Now, to add a row, we should put a semicolon between the two variables inside the square brackets, and to add a column, there should be space or comma between the two variables inside the square brackets. In the console, we see that new row and column is added to the matrix A. A sparse matrix is a matrix which has more number of zeros than non-zero entries. Scilab provides several features to manage sparse matrices and perform all the linear algebra operations on sparse matrices, which we perform on normal matrices. We can define sparse matrix using any of these functions. Let's see these in Scilab. Here, we define sparse matrix using three functions: SPI, SP0s and sparse. SPI function returns an identity matrix with ones stored at the diagonal. Zero entries are not stored. SP0s function is used to just define the sparse matrix variable, since zero entries are not stored. To use sparse function, we first define a vector which has non-zero entries of the matrix, then we define a matrix, which has row-column pair, for the non-zero entries. In the console, we can see the pattern of the sparse matrices which we defined. In Scilab, we have functions to manage sparse matrices. Let's see these functions in detail. Here, we define a full matrix A with many zero entries. Then, we convert this full matrix into sparse matrix, using sparse function. We can get number of non-zero entries using nnz function. Using spget function, we get a matrix having row-column pair of the non-zero entries, and a vector having the non-zero entries. In the console, we can see the results of these functions. Sparse matrix factorization is same as that of full matrices, with only difference that they now operate on sparse matrix. The underlying factorization algorithm is same. Linear solvers operating on sparse matrices are slightly different than normal solvers, in the sense that they have to factorize the coefficient matrix using sparse factorization functions. LU-solve function will solve the system by first decomposing the coefficient matrix into lower and upper matrices, using LU-fact sparse matrix function. UMFPACK function is an external solver available in Scilab. It is a multi-frontal solver, capable of solving systems with large matrices. That brings us to the end of this session. Thank you for your interest and attention.